All right. So probability. All right. So what is probability? To to speak in simple terms, not in like in absolute detail theory kind of thing. It is basically a study of chance. Okay. What is the probable? Probable. You understand the word probable, which means likelihood or expect something probability. What is the chance? Even though we believe that like it is from God, but according to the circumstance we observe, the pattern we observe in the like generally how it is, what is the like statistically probability? You understand from that perspective. So it is it is the study of chance, and you know, so it starts from zero. I mean, if the probability for a certain value is zero, it is not probable at all. It is impossible. Okay. If the probability is 1, then it is certain it will happen for sure. And always remember the probability cannot be greater than 1. Never. It is not possible to greater than for the probability to greater than 1. If the probability is represented in percentage, it could be 30%, 50%, and stuff like that. But percentage, we usually denote it in fractions. So in fractions or in decimals. So 50% means 0.5 or 1 upon half, like this. So in percentage wise, it cannot be more than 100%, which is 1. Okay. And half, the more you are closer from the half to the towards the certain side, more probable it will be. The chances is more probable for happening it. And the more closer you are from half to 0, the less probable for the chances it is, right? And if you are in the kind of middle ground like this, then it is equally likely. It could be either 0, like equally likely for even. For example, if it has a coin, what is the chance that it has a head or tail? 50%, half the chance, equally likely. Okay. If you have half probability, that means equally likely it can be head or tail. You understand? So let's say I say, what is the chances that it will rain? If I say the chances for rain is, 70%, that means, and if I don't tell you the chances for rain, you can still figure it out by subtracting it from 1. If I say there is 70% of chance that today it will rain, that means that it has a probability of 0.7, and the probability that it won't rain would be similarly 1 minus 0.7, which is 0.3. You understand? So there is that. Usually we use this formula to find probability. So probability we denote like this. In parentheses or brackets, the probability of a particular event. Let's say if I trying to find the probability of rain, I would write like P rain, probability of rain, or probability of head, probability of whatever the event, we name that event, equals to favorable outcome divided by total outcomes. Favorable outcome on the numerator and total outcome on the denominator. You understand? And as I've said, rain could be, you can write probabilities either as percentage, as fraction, like 70 out of 100, 30 out of 100, or in decimals. Is it clear? Let's say you have a bag. Okay, you have a bag and you have different color balls, red, blue, black balls like this. All right. And so you want to find the probability of blue. You want to randomly select a ball from here. Okay, sorry. Randomly selecting a ball from here, and you want to find the probability. What is the probability that I randomly close my eye and pick up a ball? What is the probability that a blue ball comes out of here? So that is favorable outcome, which means how many balls do you have for blue? 3 balls, right? Blue ball divided by total balls. And how many balls do you have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be 3 by 9. You understand? Similarly, for probability of red, what is the favorable outcome, which is 4, because you have 4 balls, red ball upon total, 4 by 9. And similarly for black, you have B by T, which is 2 by 9. You understand? Any questions so far? Any confusion? Seems pretty basic, right? Now we introduce with an idea called something called sample space. You will often find it using in the questions, or even if it doesn't explicitly mention you or instruct you to list to write the sample space, this is an important or useful tool that you can use for yourself to always list of all the possible outcomes in an experiment in any given question, even though the question will be absolutely silent regarding sample base. This is a tool that you can use for yourself to navigate you towards the correct solution. It's one of the rough that I love to do it myself. You understand? So what is sample space? It is list of all possible outcomes in any experiment. Sample space is the list of all possible outcomes in an experiment. Let's say we do an experiment, which is a tossing a coin. The sample space is either it could be head or tail. Total number of outcomes is 2. If it is fairing a dice roll, 6-sided rolls, there are 6-sided dice. There are different shapes, different dices, 4-sided, 6-sided, even 12-sided. You know that. So if you dice a fair means each number 1, 2, 3, 4, 5, 6 each has the same probability to for it to be drawn. If it is unbiased, this is what we call as unbiased. If it is biased, then they will always mention the probability for a particular number in the question, because you can't predict a biased or unfair dice. Okay, you always the question will always explicitly mention that probability. But let's say if it is a fair or unbiased dice roll, the sample space will include what are the possible 1, 2, 3, 4, 5, 6. These 6 total outcomes. It cannot be 1.5, 3, or 3 point something. It can't. It is a discrete, not a continuous, a fixed set of outcomes, and we have listed that here. Let's say if we toss 2 coins, then sample space, list of all possible outcomes. It could be either head, head, or tail, tail. First one head, second one tail, or the second one tail, the latter one. Sorry, the first one tail, the latter one head. So total outcome, how many do you have? You have 4 outcomes. Let's say, so what is the probability for 2 tails? So how many true tails do you have? We have 1 divided by total outcomes, which is 4. What is the probability? A head and a tail. A little different. A head and a tail. So first head, then tail, or first tail, then head. Both of these fulfill the condition for a head or tail. The question didn't explicitly mention that first should be a tail or the second one should be a tail. If that was the case, then that would have been 1/4. But since that is not the case, so 2/4 will be the probability. You understand? Any questions so far? Do not hesitate to ask any question if you ever have, and immediately kind of pause me and interrupt me. You're free to do so. All right, that's great. So probability first head and a second tail is 1/4. Similarly, if this was probability first tail, second head, it would have been 1/4. Now moving on to the fourth event or fourth scenario or experiment where a coin is tossed and a dice is rolled. So you are doing the combination of both. You are tossing a coin and you are rolling a dice. So we have total 12 possible outcomes. It could be first head and then 1, 2, 3, 4, 5, 6, or it could be tail and then all these same numbers 1, 2, 3, 4, 5, 6. So this is one condition, two possible outcome, 3, 4, 5, 6, and so on and so forth. We have 12 possible outcomes. You can also, denote this something like this kind of diagram or something. So this is 1, this is 2, and no, sorry. This is 1, 2, 3, 4, 5, 6, head and tail. You understand? So 1, 2, 3, 4, 5. So you can also denote it like this. You will end up like if you this is a bit lengthy or it takes a bit time consuming. So this is kind of less time consuming. Okay, so this thing is what we call basically. I don't remember any explicit name for this. What diagram is this called? But this is just representing the sample space, the total possible, the total possible outcomes. What it could be. So this represents the dice. The dice has one and head. This represents the dice has one and tail. Similarly, this has a dot here means it has the dice has three and head. So you have got in total 12 dots. So which it means 12 possible outcomes, if that makes sense. I think you're already familiar with a probability tree diagram, what that is. So this is for the first coin. It could be either head and then tail. And if it is a head, then and then for the second time, if you have a head, so the outcome is head, head. If it's a tail, head, tail. Here, if you have, tail followed by head, so tail, head, and here you have tail, tail. So what we do is usually write the probabilities here. So which is 1/2 everywhere, but in a kind of more complex scenario, complex, the probability changes, and we actually write that here. And if you want to reach any particular the end point of a branch, what we do is we multiply. So this thing multiplied by that. And if we consider like multiple branches, sort of, or like it could be either head, head, what is the probability that's a head, head, or a tail, tail, then we take this probability half into half, and then we add plus this half into half. I think you already should be familiar with this already, if I'm not sure. Yeah, that's great. So without spending much time on this, let's get into a much advanced and detailed things. Here you can see what a probability, a head and even number. See, if instead you like draw this diagram for this experiment, a coin and a dice. So the coin could be either head and then tail, and then you have six possible outcomes for head, six possible outcomes for tail. If this was something like first you take the dice, then it would have been like 4, 5, 6, and then again it would be head, tail, head, tail. Okay. Since the question is silent with regarding which event is actually happening first, whether you are throwing the dice first or the coin first, is just simply mentioning you're just throwing a coin and the dice. The order doesn't matter. So, like virtually, there isn't any difference between one H1 and one H. Like order doesn't matter. The combination is what we are carrying. Then in that case, like either of them should do the job. You can feel free to like choose whatever you want, whatever it makes easy for you. Okay, so the probability for a head, an even number. What is the probability that you have a head? So which means 6 out of 12, we have 6 outcomes where we have head, but an even number. So which means 2, 4, and 6. So total outcome, favorable outcome divided by total outcome. So how many favorable outcome do you have? You have 3. How many total outcome do you have? Which is 12. And if you want, you have to write the final answer in a kind of simplified, more simplified way, in either fraction or like 0.25 in decimal or something like. So it should be 1/4. This is the probability for head and like for a head and an even number. Instead, if I had asked you what is the probability that it is tail and a prime number, tell me what would that answer be? Why? Exactly. So we have got same number of prime numbers, three prime numbers. That is 2, 3, and 5. One is not a prime number. The definition of a prime number is that it must have factor only two factors, one and the number itself. So number one has only one factor, which is one. That's why one is not a prime number. So we have got three possible outcomes or three favorable outcomes over the same possible outcome. So that's why the probability would be same. Excellent to understand that. Now we move on to a bit advanced scenario or experiment. Let's say you roll two fair dice. Okay. So let's say first one is the red dice and second one is um, green dice. So here is the you have total 36 outcomes. You understand what is the meaning of this? This dot represents that you have a 5 on the first and 2 on the second. This represents that you have 3 on the first and 6 on the second. You understand? So let's say, if I were to tell you what is the probability that both has the same score, what would that be? What is the probability that both the dices have the same score? All right, exactly. You are correct. So the probability that you have both same scores, which means if the first one is 1, the second one also should be 1. If the first one is 2, the second one also should be 2. So how many possible favorable outcomes do we have? We have 6 total outcomes. So same score can only happen if they're same. So 6 divided by total outcome, 36. Favorable outcome divided by total outcome. You understand? So that's how we get, you know, 6 out of 36 or 1 upon 6. Now, if I were to tell you what is the probability that the sum of the scores is 10, what would that be? What is the probability that sum of the scores you add? Let's say the first score is 2, the second one has I think 4. So what is the sum of the scores? It is 6. What is the probability that the sum of the scores is 10? Could you please explain your reasoning? Exactly. So I think, did you just cheat from the notes written here or something? Oh, that's great that, yeah, you've solved it without seeing it. So exactly. So what is the possibility that, like, that you have a total sum of 10? You see that it could be that the first thing is 4, the first one is 4 and the second one is 6, or it could be other way around. The first one is 4 and other one is first one is 6, other one is 4, or it could be 5 5. Are there any possible combination that would like give you a sum of 10? There isn't. So there are 3 favorable outcomes which give me my answer. So that's why it is 3 upon 36. Okay. Sum is not greater than 10. This is sum is 10. My bad. It's not sum is greater than 10. Anyway, so it is sum is 10. Score is 10. Instead, if I had asked you what is the probability that sum is greater than 10, can you tell me what is that? 6 over 36. Okay, let's figure out. remember, we are trying to find a sum that is greater than 10. Okay. So if I consider this thing, so we have 6, 6. What is the sum? 12. So it goes in line. And if we have here we have 6, 5, so 11. That's also correct. And here also we have 6, 5, 11. But here we have 4, 6, 10. We don't want 10, we want greater than 10. So this is not what we want. Here we have 5, 5, 10, not possible. Here also we have 6, 4, 10, not possible. Now tell me, do I have to check all of these anymore? Because like if you observe the pattern, the more we go left, the number gets reduced, and the more we go, the more down we go, the number gets reduced. So here obviously if these things didn't work, these things are equal to 10, these things are greater than 10, this must be less than 10. Let's figure it out. 5 and 4, see, this is 9, this one is 9, 5 and 4, and similarly for all of this. So actually this one is correct, sum is greater than 10, would be 3 upon 36. So the sum that is greater than 10 is also 3 upon 36, and the sum that is 10 also get 3 upon 36. By the way, this is a coincidence. This does not mean that every time you will have the same thing. You always have to take the decisions, but after observing the given scenario and the particular like incident or something. It's not the one size that fits all. It's not that you can something memorize. You have to observe. It is a coincidence that they became equal, but that is not the case every time. Okay. So this is how you see how the sample space is helping us, how the sample space is assisting us. Now, if the question explicitly tells you draw the T diagram, draw the sample space, then you have to. If it doesn't, then I said that you can use this as a tool for your purpose, for your rough work, if you are encouraged to do so, because like you can get, if you don't draw something or write something, you might get you might make silly mistakes. It is a more tangible approach. So I would suggest that it is highly recommended that you do so. And if the question states explicitly, then there isn't any discussion. But I'm talking about those that the question only asks something like find the probability. Then you can have this as a rough work to like to just to aid you in your calculation. Like statistics and probability is really a topic, and also permutation combinations, you really get puzzled up. Like even teachers sometimes get confused when they have really hard questions. Like you have to have your minds in a cool environment, and you really have to think and consider all possible scenario. You will experience that while you solve that. So you have to be really careful. All right. So now we see a 12-sided dice. Let's say you have two 12-sided dices and you roll this. Now, what is the sample space? You have 12 on this and 12 on this. Oh no, you don't have to draw 144 dots. That's like too much. Instead, let's see what is the question. What is the probability that the product of both scores is 24? Can you try and find out what is the probability that the product of both scores is 24? No, the probability is not 1 upon 44, 1 upon 144, because what is the probability that the product of the both scores is 20? So you roll this dice and you also roll this dice. The thing that you observe here, you multiply that with 24. So is there only one possible way via which we can get 24? You can get 2 into 12. Also, you can get 12 into 2. You can get 6 into 4. You can get 4 into 6. All of these are like the possible ways you can get a product of 24. So why do you say 1 upon 24? 1 upon, like 1 upon, yes, 1 upon 44 would be something like, if they ask you, yeah, 12 into 12, like product, what is the possibility of product of 144? That is only possible when it is 12 and 12 and nothing else. Then you would have said 1 upon 4. So what is the probability that the product of both scores is 20? The easiest way to solve this is kind of find the all the factors of like 24, something like 1 into 24. This is not possible because we know that the maximum number is 12. So 2 into 12, then we have 3 into 8, 4 into 6, and then you need to consider the other way around. So 2 into 12, 12 into 2. You understand? So you find the, I think it's called the HCF or LCM. I'm not sure. Like the fact you factorize and find out all the factors. Exactly. So the product probability the product is 24. You have 6 favorable outcomes. So that means 6 out of 44, but you have to write it in the like simplified, most simplified. So 6 1 upon 24. Yeah, you are rolling the dice once, but it is also possible that the first one has 8, the second one has 3, or it could be that the first one has 3 and the second one is 8, the second one is 8. You are rolling both of them once, but I'm thinking of probability, chance. So you have to consider both of these as like two different instances where first one is 8 and then versus the second one is 8. We are treating both as separate dices, even though we are not saying that like dice 1 and dice 2, we have two distinct dices, and here the like order really matters. Here order, like which dice has what value, is really what we are considering here. Like even though like this question is just not a standard question. In the question they would say the like key two dices, first dice and second dice, then it will be treated as a separate dice. All right. Any confusion or any problem you have so far? Okay. So um, now here's the thing. Since we cannot like the sample space is kind of really good thing, but since we cannot make sample spaces for bigger experiments, just imagine this is 12 and 12. So do we just place 144 dots? Like sample space, it's not feasible. Since we cannot make sample spaces for bigger experiment, what we do is called listing. Listing is a proper technique. We list the something like this, the all the possible like ki bole, all the possible favorable outcomes. You understand? Listing is a proper technique when the experiment is really big and we can't really write all the possible outcomes. Okay. Also, you are already familiar with tree diagrams, and I've already mentioned to you the rule of that. So first rule is sum of all branches emerging from one point is one. Sum of all branches emerging from one point. So this is one point. The sum of all branches, this thing plus this thing plus this will always become equal to one. Similarly, sum of this is one point, so all branches emerging from this point. So this thing and this thing will also equal to 1. So if I just tell you that I just remove this value and tell you to find the value, what you can do is you can subtract 1 minus this value and then you will get that value. Okay, this is the first rule. Sum of all branches emerging from one point is 1. Rule 2. If you want to find the branch total probability, then we multiply. So what is the probability that it is raining and I go to school by walking? 7 by 9 into 1 by 7. Okay. And rule 3, if you consider more than one branch, you have to add individual totals. So what is the probability that it's raining, I go to bus, or it's sunny, I go to bus? So I'm considering both of these. Like when we use or, when both cannot be combined. If they can be combined, we use and, we use multiply. So it's raining and I am also using the bus. So both of these events are happening simultaneously. Like this is like and condition, so we multiply. But when we say or, we have to you have to give plus. So what is the probability that it's raining, I take and I choose bus, 7 into 9, 7 by 9 into 2 by 7, plus it's sunny and I choose the bus, which is 2 by 9 into plus 2 by 7. This is how we do. You understand? I will touch the Venn diagram briefly today. It's not that a big deal. It's easy, I think, if you remember the set theory. It's sometimes it helps us like solving questions. So don't worry. I will also get into that. Now I am giving you 3 minutes to solve these three questions. Okay, you have the probability given here, and you have to find the probability that it is raining, rain and bus, probability cycle, and probability not cycle. So you have got all right, so let's see the answer. Please check whether you have got the same answer or not. So wait, I think this, yeah, this is the solution. You got it right? Okay, that's great. Let me give you another one. All right, so this is the solution. You have the same working. All right, so that brings us to the end of our session, except for a little thing I wanted to uh, focus, even though it's not explicitly required, but understanding the understanding the concept would be very much helpful. So let's say you have a probability. Let's say if they give you the probability that it will rain is 0.78. Let's say probability that I go on a bus on any given day is 0.32. Okay. So here is the twist. If I tell you to find the probability that it is raining and I go to bus, what will you do? Will you just like I go I it's raining, or I go to bus? So now you see, I told you that for or you use plus, but if you add these, it is becoming more than one. So how is that possible? Probability cannot be more than one. Here is the twist. when you have when you want to find OR of two probabilities, you if you imagine the Venn diagram like this, so let's say this represents rain and this represents bus. So there is also an intersection. If you remember the notation, or means we are talking about the union. So probability of R union B. Okay, you're talking about the entire entire shaded thing except for the outside thing, entire this portion. Okay, and this inside thing is what we call intersection. In set theory, we usually denote it as R intersection B. Okay, and the reason why adding these two gets more than one and does not give you the answer, because when you consider let's say you consider R. Okay, so if you consider R, then what happens? You take you let's say so you take these red portion. Okay, this is the probability that is included in R. But when you also add P, what happens is you just take the union twice. Do you understand? You take the intersection twice, which is a wrong calculation. Why are you considering intersection twice? That's why you have to subtract the intersection R intersection B once from here. You understand? So let's say the probability for, like, it's raining and also you also use bus. I'm just making this up. It's not any standard question or something. And bus is something like 0.22. Okay, then what you have to do is, for this one, 0.78 plus 0.32 minus 0.22. Now it would be 0.9. This would be the probability. This is what it has said there. If you are considering or union, and if you given the probability for each individual events, then you also have to subtract this thing. You understand? My main like my main focus was to like show you this thing, this concept. Okay,